This episode is brought to you by Elevate AI. Are you looking for ways to integrate speech-to-text functionality into your contact center application? Do you often need to convert a lot of audio into text? Well, Elevate AI provides 1,000 interactions of AI-driven transcription per day free of charge. You'll get access to models built over 20-plus years with billions of interactions, and great features like social security number and credit card redaction. With a few lines of code, developers can integrate Elevate AI's API into your app. Check out their GitHub repositories for examples and the SDK. It's free to sign up and no credit card is needed. Head over to elevateai.com/HanselMinutes to get started today. That's elevateai.com/HanselMinutes. Hi, I'm Scott Hansel, and this is another episode of Hansel Minutes. Today we're chatting with Oren Eini, founder and CEO of RavenDB. How are you, sir?
I'm doing very well, thank you.
So I'm looking on the RavenDB website. This is a NoSQL, NoSQL document database, and you're on version 5 point, what now, 5.5?
5.4.
5.4?
Yeah.
And when that's 5 major versions, so I assume that you're making improvements every major version, something major happens. Are the major things usually performance? Or are the major things usually features, or a combination of both?
It's funny. Every single feature, every single release from the get-go, we had at least a few entries that says better performance. I've been doing that for close to 15 years. I'm still improving performance. And it's really interesting when you look into that, how much can improve performance? And you always have new capabilities, new insight into what you can do. In many cases, you have better capabilities. But at the end of the day, it used to be the case that when you develop your software, you could assume that by the time you shipped, you would get better hardware. And that would cover, any issue that you made. Now we are in a position where I'm running my code on virtual machines in the cloud that cost less than $5. And that means that I have 1 or 2 CPUs and 1 gigabyte of RAM, crappy disk, and I still need to be able to provide great performance. And that leads to a really interesting dilemma of, okay, what am I optimizing for and how? There's also another aspect here with regards to performance, which is I don't care about just raw performance. How fast can I complete something? I also care about the overall latency and batch rented. And those are all things that lead you in very different directions.
If you were using like raw hardware, the way Stack Overflow for so long has refused to go to the cloud, they're a performance-obsessed company. We've had Roberta on the show to talk about it before, and I've worked with some of the Stack Overflow folks. They're squeezing milliseconds out while simultaneously throwing more power at it. So they kind of get the best of both worlds. When we went to the cloud, I think we were all kind of fooled that we'd have that local desktop PC performance or the pizza box performance, but they really are kind of slowish machines in the cloud. The cloud is kind of sluggish. There's a lot of latency. There's latency on the disk. There's latency on the network that we don't talk about.
Yeah. Take a great example. You can take an awesome machine in the cloud, D416 in Azure. And then you realize that you pair that with a 64 gigabyte disk because this is all you need. And the latency of talking to the disk is horrendous. So you go with the premium ultra disk and you realize that you're paying amazing amount of money for this. And then you go to Newegg and you look up what it costs to get a new terabyte NVMe drive, and it costs you less than, $100, $200.
But I'm holding up a Samsung 990 Pro I paid $150 for.
Yeah. And try to figure out what is the IOPS rate for that. And that should be something in the order of hundreds of thousands per second. And a rate that in most NVMe today can exceed the rate of SATA. So you're actually limited by the bus that you're using over the capabilities of the hardware. And then you go into AWS or Azure and get the most amazing disk that you can have. It's going to cost you tens of thousands of dollars a month, and it can compare to 150 disk.
Okay, so then is the trick now when we hear the word cloud native, or I prefer the term cloud aware, and I think of those things as being separate concepts. A cloud aware application is one that is conscious of the fact that it's in the cloud and then is written with the cloud in mind. So it's going to know about these latencies and it's going to do the right thing, which will be a different thing than if it were running locally.
Okay, so let's talk about this. Regardless of where, so let's assume that you're running a business application. That's a simple scenario. One of the key metrics that you measure on is latency. And they've been studied by Google, Google and Amazon on performance, on latency. And Amazon realized that adding 100 milliseconds to the page load time has an impact of 1% on the bottom line. And 1% is huge. And 100 milliseconds is so small that most people can't even perceive that. So you absolutely want to have as low latency as possible. But now you're running on, let's say, GP3, which is a AWS disk. It has latency in the single-digit milliseconds. Doesn't sound like a lot. In fact, it sounds like very fast. But you realize that, again, if I compare that to a local SSD or NVMe, I have sub-millisecond response times with hundreds of thousands of operations per second. Now, I build databases for a living. So when you say, oh, I'm cloud aware, I have to be able to adjust what I'm doing, that's kind of how do I make reading from this faster when I'm limited by reading from the disk?
Well, would you not then think more about using more memory? I mean, I've always in my much simpler applications, I do very aggressive caching because I feel the one thing that we don't give the cloud credit for is that the memory is cheap and the disks are slow. So I tend to have high memory systems, medium or low end CPUs, and I don't really worry about disk speed because I cache gigabytes in memory, which is a simplistic way of doing it, but it solves the problem for me.
It is an amazing way of doing that, and we do that. But our problem is actually the other way around. RavenDB is a transactional database, which means that in order to commit a transaction, I have to ensure that the data hits the disk. And that leads to a whole new nest of worms. Because I have my contract with my user is that I'm going to keep the data safe, which means that I have to hit the disk, which means I have to accept the latency for that. And then you start playing all sorts of really interesting tricks with how you do that. For example, are you writing the data in a sequential manner or random manner? Can you delay the writes in some way? One of the things that RavenDB does is merge different transactions. So think about this scenario. You have a system that has a high load. So one of the things that we can do is says, okay, you send me a transaction and Joe sent me a transaction. What are the guarantees that I have to give you that your transaction is atomic? But I don't have to give you a guarantee about the order of different transactions because I only have to have the order within a particular transaction. And I can play all sorts of really nice tricks. For example, I take your transaction and I merge it with Joe's transaction. And I only have to go to the disk once. And that alone means that that feature bumped me from 2,000 requests per second to 20,000 requests per second.
But doesn't that imply that I could just be happily sending transactions and then have one fail and not know why because it was a neighbor? Aren't you creating a noisy neighbor problem?
No, that's the fun part. We are still talking about transactions. So let's say that your transaction failed. What happened to your transaction?
Well, I assumed he was along for the ride, right?
No.
So he merged. No?
Well, yeah, we merged him. He operated on top of your system, your changes. Mm-hmm. But what I have to do now, I only have to do is roll back your changes and then rerun his transaction on top of the clean state.
Ah, okay. So he isn't affected. So in the best case scenario, you get perf. In the worst case scenario, he goes as before.
Yes. At worst case, there is some additional latency to resolve this, but this is quite rare. So the beauty of this is that you suddenly have the ability to massively increase the amount of operation that you do. Because the limit is how often I go to the disk. And I love giving the example of going to the store. If you need to have a cup of coffee and you need milk and coffee and sugar, you can go to the store once for each one of them. And in terms of total amount of money you will pay, it's the same. But the amount of gas, amount of time we spend just going to the store is horrendous. So you don't go to the store the moment that you have something that you need. You wait and maybe you even speculate, oh, I know that I haven't run out of rice yet, but I will be soon, so I will already go and get some rice and things like that. So there is a whole science about trying to figure out what's going to happen next. Should I wait just a little bit longer to gather more transaction and how much of other stuff like that?
Interesting. Okay, so let me ask you this, because I feel like people don't talk about this enough. I'm going to use .NET as the example, and then you can use Raven as the example.
Mm-hmm.
A new major version comes out, and we say, we're 10 times faster at this, or we're 11 times faster than that. And we all clap and we applaud how wonderful it is. But no one says, wow, did we suck by an order of magnitude before? We don't look back. Like, we're getting impossible speed improvements. And it makes me wonder, well, what did we miss? I assume you have similar experiences in Raven.
Yeah. So the typical answer is you look at the death by 1,000 cuts. And I'm going to, let's use .NET as a great example. Let's talk about what it means. Go to 2008, so 15 years ago, and I found a bug in the .NET framework.
Okay.
What do we do then? At the time, I'm a Microsoft MVP, so I can call the team. I can open an issue to connect. I can do a whole bunch of stuff. That goes into some bug database. It gets triage. Let's say that I got confirmed, yes, this is a bug. Yes, we'll fix it. It will ship in the next service bug release in 6 months. People who can see my face can see that I'm just want to tear my head off. And that was a common experience.
Mm-hmm.
Move to .NET Core, and suddenly this is an open source project. And more importantly, it accepts contributions. So now here's the deal. I now run a benchmark on my end, and I can see that there is this method that is allocating too many strings. So I can optimize that. For example, parsing dates. This is something that is quite expensive, and if you know what format you want to do, you can do that far more efficiently. And someone contributes that to the .NET framework. And that is not a major change. Parsing that is not what your application is doing. But then someone else does a slightly better string index of optimization. And multiply that by enough time and enough people, and you start seeing amazing results. And it's even beyond that. Let's go and look into what sort of feedback cycle you create. For example, let's talk about a language integrated query, an amazingly complicated piece of work. And in general, if you look at the Roslyn guidelines, they say we are not allowing you to use link inside of Roslyn, which is funny because Roslyn is how you implement link. So what's going on? Well, the problem was that at least at the time that guideline was written, all of the link operation allocated. And that in turn means that you have a high cost in performance down the line. Now, someone says, "Oh, I love to use, contains on an index, on a list or something like that, and let me add a specialized code path just for that." And you start adding a lot of dedicated code paths specific for that. And suddenly you just upgrade, and a piece of code that used to allocate now does not. The impact on performance on that particular instance is not that big. Allocation is fairly cheap. But now you're saving GC cycles down the line. And then you have something even more important. Let's talk about string index of. So I want to know, given a string, I want to know if a particular substring is inside of that. That happens a lot. Like a lot. And what happens then? Well, it turns out that you can do that in a lot of ways. One of the ways that you can do that is the CS computer science classic, do a loop, do a check, something like that. And then you realize that there have been little PhD written on the topics, or PhD written on the topic. And what is more is that you now have the ability to specialize that. The modern CPU have a specific instruction to do parallel search inside of a vector, inside of a set of characters, and you can do that as one instruction over 16 characters at a time.
So a parallel search across a string. So someone at the very high, so when we think of low level string work, which is not low level, it's string.index of, you're saying that when that gets optimized all the way down into the silicon, we roll, and then you're in the middle of multiple for loops, or you're in the middle of something complicated. These little, like, this is the whole, a butterfly flaps its wings and a hurricane happens in Brazil.
Yeah,
so, but the opposite of that.
Yeah, try to imagine if you think about how index of is implemented.
Yeah,
you probably think that, okay, I know how it's implemented. There is a for loop, you scan it. Okay,
yeah, just run down the string looking for it.
Yeah. Now, then you realize that, okay, how much code do you have in something like that? Well, not that much, but if you translate that to machine instruction, it's probably few dozens to low hundreds of instructions. Okay, so far so good. Mm-hmm. But now you optimize that to a tight loop that is maybe 10, 15 instructions using a dedicated assembly command just for that particular scenario.
Right.
And suddenly the code is much more efficient, but then you have another impact. It's much smaller, so it has better inline so it's able to inline the method. And if you're able to inline the method, then you just save a method call. Now, what's the cost of a method call? Well, you have to save the registers, do a call, jump to another location, a whole bunch of stuff like that. Or you can make it as a single set of compact instructions that the CPU can just glob in one shot. Now, you start making those sort of changes, and it has an impact both on the code base itself, but also on the way that everything else works. So if you look at the changes that happen to C#, we have span. Why do we have span? Because we didn't want to allocate, so we needed some way of actually avoiding doing those allocations. And then you have UTF literals. And then you have a collection marshal, for example, which allows you to get a reference to the value inside of a dictionary. So if you want to mutate the value inside of a dictionary, you don't have to do two lookups. And those are all things that for high performance code use a lot. None of them are rocket science. But they just take a lot of time, and they are paying compound interest.
Okay, that's a really good analogy. Compound interest is one of those things that, as humans, it's just hard to consider that 4%, per period adds up to ridiculous improvements. But when you're doing all of that in order n, in tight loops, you're getting benefits from .NET. You're getting benefits from your own work. So it's the combination of your own algorithms improving, plus silicon improving, plus .NET improving, and it all adds up into compound interest. That means performance for everybody.
Yeah, and it's even better than that. Think about that. every time that you make a change that has a performance positive impact. So you save 1% here, 2% here, 1% here, and they're additive. And now you start getting into all sorts of secondary implications. Going to the index of that I gave before, that index of used to have a whole bunch of conditions, of branches. And now we're using dedicated instructions, no branches. And from a performance point of view, that becomes super critically important. Here's another really interesting thing that happened recently. The .NET team added intrinsics into the framework. So now I'm able, from C# to write code that uses AVX instructions. So to give you some idea, I recently spent almost 2 months head down implementing an integer compression algorithm. And the way that I did that using an algorithm called Seemed Fast Before, written by Daniel Amir. And he wrote a whole bunch of absolutely incomprehensible C code. Average method length, something in the order of 300 to 400 lines of code, full of basically nonsense. After I figured out what he was doing there, I was able to go and implement something similar. I was able to use operator overloading, and I was able to use the intrinsics to create code that is simpler, faster, and much easier to operate. It generates amazingly good code.
Let's dig into this a little bit, because I think there's some folks that have been paying close attention. We may have lost them. So we're talking about AVX, right? We're talking about advanced vector instructions. These are ones that have been, they're in addition to ones that used to be part of the legacy SSE instructions. These are, CPU specific instructions. CPUs support AVX instructions. They support AVX2 instructions. SSE was streaming, SIMD extensions, which is an acronym within an acronym, which is single instructional, multiple data, right? So this is parallel processing that we're talking about. And these instructions have been available on x86, x64 in various formats on various CPUs for a while. And the core CLR, the thing that is making .NET work, requires at least SSE2 and above. And now that AVX is available to everyone, the .NET Core starts to expose that. Now, here's my question, though. Is .NET a high-level framework that should hide these things, or is this...
Hell no.
It should not. So you said no. This is a great thing that it's exposing the silicon to you.
Here's the deal. Let's talk about something simple. I want to do some high-level operations. For example, I have a list of numbers and I want to sum them. Mm-hmm. That happens, every now and then, wanting to sum some numbers. So I have 2 ways of doing that. I can write a for loop and sum them one at a time. And the cost of that is O of n. I can also use AVX, and instead of summing them one item at a time, I can sum them 16 items at a time. So the cost is n divided by 16. I can multiply my performance, and the amount of time that it takes is 1/8, 1/16. It's that good. You absolutely want to have that level of control. And it's actually kind of amazing if you think about it, because how are you actually going to write something like that? Because this operates on unmanaged buffers. But with .NET today, I can give you a list of ints, and you can, without writing a single line of unsafe code, without understanding pointers, nothing like that, you can write vectorized code that process something in parallel in a very easy and cheap fashion.
Mm-hmm.
And the performance improvement there are absolutely huge. To give you some context, the integer compression algorithm that I implemented is fast enough that I don't need to worry about its performance. I can do 1 billion integer decompressed per second. And this is before I got to the real serious optimizations.
Mm.
I cannot do that without going to scalar instructions, without going to vector instructions. So scalar code, the normal code that you're familiar with.
Scalar code, as SCALAR, right?
Yeah.
Right. When you add a scalar to a vector, you can do it in a for
No,
loop.
so if I'm doing additions,
Okay.
so I want to sum a vector. Scalar code is going go to 0, go to 1, to 2, to 3, etc.
Right.
Vector code is grab a vector of the first 8 elements, sum them with the next 8 elements, and then sum them with the next 8 elements, etc. It's a really funky way of thinking about how this is working. It can be incredibly complicated, but it pays off because it moves you from hundreds of thousands of operations per second that you can do to literally billions. And being able to do that in .NET natively is a huge impact because we tested shelling out to a C library, and the p-invoke cost is absolutely horrendous. We don't want to pay that, so we actually had to spend the time in converting that into managed code to get the most benefit out of that. This is not something that you pick in the afternoon, but it is absolutely something that you want if you care about overall performance.
So are you calling these intrinsics? Are you saying if AVX is supported, use this intrinsic, if SSE is supported, or are you only working on CPUs that have the support? Do you do the software fallback?
I have a software fallback, and there are 2 reasons why you want to have this software fallback. One is that in many cases, the vector version is nonsensical in the extreme. So try to imagine that I hand you an internal combustion engine from the 1940s, and you could more or less figure out what's going on. It's big, pieces are moving, but you understand what's going on. I give you a modern one, and your ability to understand what's going on is basically nil without spending a couple of years in study of that.
Mm-hmm.
And it's very much the same way with vector instructions and vector code, because there is so much that is going on all at once. And another impact that makes it really complicated, you can't express everything in an easy fashion using vectors. So you use a lot more of lookup tables, and you use a lot more of esoteric instruction in order to achieve what you want. So the typical way to build such an algorithm is you first write the scalar code, the obvious one that is for loops and operate on one element at a time. Once you've proven to yourself that this is accurate, then you go and write the real thing using vector instructions. But then you realize that, oh wait, there is still a problem here. I'm now running, let's say that I want to run using AVX or AVX2. Pretty much any x64 CPU in the past 10 years or so shipped with AVX2 at least. By the way, I have a couple of high-end machines right now that I'm sitting next to it. They don't have AVX 512, for example. So even though it's out for 5+ years and I have modern machines, I don't actually have that. They tend to be only on server machines. But AVX2 is really, really common. But so I can rely on that and assume that, hey, this is going to be there. Especially I'm building a database, I can dictate to some extent what you're going to run on. But then there is another aspect. I'm also running on our machines. And I was running on Raspberry Pis in 2018 when you had to recompile the .NET cores on ARM, which was not so much fun for my team members. But that means that AVX is limited to x64. ARM has a completely different set of instructions, which means that you have to write really, really complicated code there as well, except that you don't have to do that. And this is where I really like the implementation of .NET, because you have layers of operations. You can write normal code, and the compiler sometimes is smart enough to vectorize your code. Or you can use vector types, vector 64, vectors 182, 128, 256, and vector 512. And those numbers refer to the number of bits that you have in the vector. And you can take a vector of 256 and treat it as a set of 4 longs or a set of 8 integers. And you can do vector operations on that. You can add multiple vectors together, and that would generate the appropriate vector instructions. So what we're actually able to do is to implement this integer compression routine using only the high-level vector instructions, which means that on the one hand, I get really tight AVX2 code, and I also get SV, which is the equivalent on the ARM, the scalable vector extensions, when I'm running there.
This level of understanding I find fascinating. I feel like you use the internal combustion engine analogy, which I use all the time, because we live in a world where people expect software as a service, which RavenDB provides, which is basically Uber. But sometimes the internal combustion engine breaks down, and we got to go figure out what's going on. And I love that you geek out about both having a great software as a service implementation, but also, hey, let's build this engine from smelted steel that we made ourselves. Like, let's go into the mines and talk about how to make metal. That's so fun.
At some point, we got to the point where we convince a rock that it can think.
Yep. We infused it with lightning, and now it thinks.
Yeah, but it's funny. I spend a lot of my time trying to optimize things to get the extra millisecond or two. And then I realized that, I have this wide open field here of, okay, let's do vectors. Let's do, let's reduce allocation by 16 bytes per operation. That means that we saved 3 gigabytes, and suddenly the GC isn't a measurable impact on my performance. And you see a whole bunch of impacts like that, and suddenly you have you see it in the graph, in the CPU graph. You see, okay, upgraded, boom, we have a major shift down in amount of resources that we take. So we can take bigger load, we can take smaller machines and things like that.
Very cool. Well, thank you so much for chatting with me, Oren Eini from RavenDB. If you like this level of performance in your products, definitely check out RavenDB. This is a proof of the kind of folks that work for you, I suspect, that are this obsessed about performance. I've really enjoyed reading your blog for the last 15 plus years and living vicariously through your building of your company and this great product. Thanks so much for chatting with me today.
Thank you for having me.
This has been another episode of Hansel Minutes, and we'll see you again next week.